Hello everyone, I'm Oz, and this paper is main product detection with graph networks in fashion. So first I would like to start with what is main product detection. It's the most important step in the fashion feed parsing pipeline. So as you see here, we have multiple images and we have a product title. And to parse the product, we input these images into a fashion object detector. This fashion object detector is able to detect the fashion items in images. And then by using the product title, we should be able to determine which bounding boxes have the main item that is being sold. In this case, it's the cardigan. And then we can use this, since we parse the input, then we can use this bounding boxes to extract features to be used for any other task like visual search or attribute extraction or any other task. So if the main product detection fails, then the output would not be the desired output in the following steps. Therefore, it's the most important step in the pipeline. So this first mentioned in this work, and this was the model that we were using. They were using a word-to-vec model to get the sample to get the title embedding. And then they were using AlexNet in order to get the image features. At the end, they had two classification losses, two classification losses for image and text classification, and one contrastive loss for image and text pairs. So they were trying to reduce the distance between the positive pairs and increase the distance between the negative pairs. So but the problem is that they were not using any. They were treating each image independently. So as you have seen in the previous slide, there are multiple images in a product, but they were not, the context of other images were not taken into account in this work. But in this work, we propose to represent all bounding boxes as nodes in a graph and incorporate graph convolution networks. As you see here, we represent them as nodes in a graph, and they are the graph is densely connected, which means all nodes are connected to each other. So this is our model, and this model is actually inspired by the work that you see in the bottom of the slide. So first we start with two branches. One, the BERT model is the multilingual model, and we also use BERT tokens in order to tokenize the titles. As you know, the tokenizer just gives tokens, and the BERT model outputs embedding storage token, and then we use average max pooling in order to get the product title embedding. And then we have a ResNet34 model here in order to get the image features of bounding boxes. And then we concatenate these features and embedding, and then input this to a message runner. The message runner is important because, as I said, the design is fully connected. Therefore, we cannot just sum the features of neighbor nodes. So therefore, we should learn the message passing of the graph. So for that, we use the message runner, and it consists of two fully connected layers with ReLU, and it gets the concatenated features. And for each sample, it outputs a feature, which is shown as EN. And when this when these features for each sample, for each bounding box, are stacked together, we get the matrix E. And the multiplication of this matrix E with its transpose gives us the adjacency matrix. And then we can use this matrix in order to update the node features. This is the main thing that we do, but also we have another variant. So we also learn, instead of working on the features itself, we add additional head to graph learner in order to output features apart from EN, which is shown as DN. And these features are again stacked together in order to get the matrix T. And the matrix multiplication gives us the adjacency matrix again, and then we use this matrix to update the features. And in the next step, we have a graph network, where the node feature update happens. and it consists of one fully pointed layer with a leaky array. And then at the end we have the node classifier. But before the node classifier, we also concatenate the text embedding, original text embeddings with the updated features. And then node classifier is just a fully pointed layer with output of 2 dimension in order to classify the bounding boxes. So the dataset, it consists of 60,000 products with bounding boxes from a fashion object detector. These bounding boxes are computed before the training. And it's aggregation of 5 different fashion product feeds in 4 different languages, which are English, Turkish, Polish, and Russian. So the average number of images per product is approximately 3. We use PyTorch and Deep Graph library. And although we have the titles in 4 languages, since we use a multilingual BERT model, we translate all the titles to 10 languages, which include the 4 languages that I mentioned. And we use them randomly during the training. We do that because we think we see that the multilingual model generalizes better. It gives us the more stable training. We see less oscillations on the validation set. Therefore, we use more languages for the training. But for validation and test, the titles in the original language are used. And our metric is accuracy score, which is 1 if all positive and negative bounding boxes are classified correctly. It's 0 otherwise. So this is I would like to go on with the experiments. So these are results, and I would like to first explain the BC model. It stands for binary cross entropy. And the difference between BC and our model is just there is no any interaction between the bounding boxes in the BC model. So it's exactly the same model actually. The number of layers are same, the layers are same, but since there is no any graph or node interaction, there is no adjacency metrics. So there is no any interaction between the bounding boxes. And the contrastive model is the one that I mentioned in the related work, and you see the two variants of our model. So in here, it's clear that we surpassed the other models, but also I think the difference between the BC model and ours is important because we really surpass by at least 4 points, and it's actually the same model. But to have this context of other images in a product, it really helps, and this is what it shows to us. And we do in another experiment, which is although we train with titles, with titles and translated titles during the training, we also would like to evaluate our models in the test when there are no any titles input. So the embeddings are just 0. And as you see, all the models, the performance of all models decrease, but the decrease in the BC and the contrast model is harsher. It's because without title, actually they don't have much. But in our case, without title, we still have the context of other images into account. The context of other images, we can take into account. And we can, although the performance decreases, we can still use this information without the title. And we also do another small experiment, which is for the BERT model. We try different pooling methods. As I said in the model slide, we do average max pooling. And it's basically averaging the nodes, the embeddings of the tokens, doing max pooling on the embeddings of the tokens, and then concatenate these 2 features. You know the average and you know the max. The sentence token is the token that is used for in the original paper of BERT, but also the authors state that it's better for specific tests. It's better to use actually some pooling methods. And we actually, we also see we see the same thing in our experiment. So that's all. Thank you for your attention.